This is a talk about, like a couple of years ago, I gave a talk on using the HP prime on the particle swarm optimization algorithm, and it's in the same family as the evolutionary. Somebody was asking how did it all start? It started with genetic algorithms by the mathematicians mimicking genetics, and then that opened the floodgate. I mean, there are probably tens and tens and tens, I don't want to say 100 and exaggerate, but of algorithms. Wikipedia lists them, and I try to go through all of them, and that's a near and impossible task. The evolutionary algorithms are very interesting because they mimic initially the genetic evolution, but they mimic the behavior of animals in foraging and gathering food and surviving. They mimic ants, bees, ants, and other insects. They can also mimic natural phenomena. I mean, the imagination is rich in all these mathematicians who mimic systems that can yield an optimum solution of a function with multiple variables. One of the main things these evolutionary algorithms have in common is rather simplicity, relative simplicity of the math of it. They may use matrices and all that, as I will show you, as I will, but there's no matrix inversion, unlike the legacy optimization algorithm based on Newton, Marquardt-Levenberg, and so on, Powell, and there's a whole 4 or 5 stuff. You can see those coded in my website. So these are very easy to code. They use a lot of random numbers. So they're not deterministic, and often you run several times and just get the best solution, with the one that gives you the least, if you're minimizing the least function, if you're maximizing the most function. So, as in every evolutionary algorithm, almost all of them, you define, you have a function with multiple variables, and one of the first things you have to do is define a trust region. A trust region is made up of ranges for each variable. So you know that the solutions that are valid, or the solutions that I'm interested in, are in this region. Anything outside, I will ignore. And then this algorithm basically, let me sum it up. Basically, you have a number of pods. Just imagine they're landing pods, landing somewhere, and they're landing at random location. And each pod, they open the pod, and all these little scouts come out, and they start looking around for the best, a better value of the function than where the pod landed. That's basically it. And then there's a tally of what these scouts found versus where all the pods are to locate the I'm going for the minimum. Maximum, you can do like a minus, give it a minus function sign, put a minus sign in the function. So anyway, so we start by calculating a random, calculating a random pod location within our trust region. And then we start the main, this is like a bird's eye view of the algorithm. Repeat, we update the pod locations. Why? Because that will guarantee that the scouts, because in the end I'm merging what the scouts bring me, function values, that will guarantee that I'm not cornered in a local minimum and skip the global minimum. So this kind of gives me like a step to, let me this says, let's check out what else is out there. It's an insurance policy against being cornered in a local minimum. And then for each pod, I calculate the location associated with the scouts in the vicinity of that pod. And then I merge the locations of the pods and the scouts, all of them. And then I sort the merged locations based on the function value associated with each coordinate, set of coordinates. And I do this for a set number of iterations. That's very typical of evolutionary algorithms. Sometimes you can add additional, like if my function value falls below whatever value, you can do that, but people just go with the flow. Say, give me 1,000 iterations, 10,000, whatever. The more difficult the function, the more iterations you have, and the more populations. These are the two main operational parameters is that you the user, tweak it, play with, is the population size. The more population size, the more random locations you're scouting, and the more iterations, the more time you give them to look for a better solution. Each algorithm has its own little coefficients that you tweak. That's on a different level. But usually the researchers have found the optimum values for these coefficients, and you just go with the flow, unless you want to do your own research. And then we return the best pod location as the optimum point. This is sort of the bird's eye view of the algorithm. So the algorithm has many parameters. First of all is fx, the optimized function that takes an array of variables, and then an array of ranges defining the trust region for the variables. So we know it has to be within this, these values. Anything outside, we will generate a random value within the trust region. The number of variables n, and then the initial step size, init step, and the final step size, fin step. And this value influences the accuracy of the optimized variables. Comment here. The initial and final step size, in my case here, is a scalar. I'm assuming that all the variables have about the same magnitude. But if the magnitudes are significant and the accuracy, then we need to make these arrays. And you supply an array. And the code is, you have to tweak the code on your own. It's a little bit more, it's not the end of the universe. You can do that easily. But they have, if it's different, the magnitudes, then these need to be arrays. Otherwise, we leave them as scalar. And then there's the maximum number of iterations, max iter. And then here we have the population size, the max pop. That's the number of pods we're launching, okay? And then the scout population size. For each pod, I have max scout pop. So each pod releases that many scouts. As you search, as you're searching, and as you're getting closer and closer to the answer, you don't want to search far away. You want to search around to fine-tune your solution. So I use a decay factor flag, B semilog decay. When that B semilog decay flag is true, the algorithm uses a log linear decay in the step size, going from the initial value to the final value. If this flag is false, it uses a log decay, going from the initial to the final. Earlier studies showed that a linear decay was not really good, was not very efficient. It did not, it impeded converging to the solution we wanted. So the algorithm has no linear decay factor. And then we create a population pop with max pop rows, that's the number of pods, and n+1 columns. So the first n columns represent the n variables Each row is a population member, and the columns are the values in that row. And then I store the function value in column n plus 1. So I have a slightly augmented matrix. The reason for this is that when I want to sort the rows by function value, it's easier that way, especially if I use something like MATLAB. There's a function called sort rows. I give it the matrix and the index of the column I want to sort for, n plus 1 in this case, and it will sort it much easier than if I had the variables in one matrix and then the values of the function values is an array. I sort that, and I need to track in which order things got moved and rotated so I can rotate the matrix. Big headache, in my opinion. Some people do it with, especially with the MATLAB commands, but if it's not MATLAB, it's a Herculean effort. So I'm choosing the easy way out here. Then I create a scout population associated with each one pod, scout pop, with max scout, with max scout pop rows, and again n plus 1 columns. The n plus 1 column has the function values, and then the first n columns have the values for each scout coordinates. And then I fill in the first n columns pop with random values that fall within the trust region, and then calculate the function value of max pop rows and store them in the in column n plus 1, as I say. Then I sort, this is part of the initial preparation. I sort the matrix max pop using the values in column n plus 1, which has the function values, and this yields the best guess in row 1. Row 1 has the best, the locations of the best value so far, and the function value, the best function value. And then this is the initialization. Now I get down to brass tacks business. I repeat with an iter variable for 1 to max iter. And the first thing I do is control the step size. And I look at my B semilog decay flag. If it's true, then I calculate the step size using a log linear method based on init step, fin step, iter, and max iter. If not, I calculate step size using a log decay mode using the same variables here. Then I go over the main pod locations from the second one to the last one. I keep the first one protected because I don't want to lose my best bet so far. So I calculate location function for a candidate for row I. This is a candidate, we're not sure, okay? Now, if that candidate has a smaller function value than the member in row I, then we replace it. Oh, we found something better. And then we sort the matrix pop using the values in column n plus 1. Again, any update, the best row will be in, the best values is in row 1. Why do I do this? This is my guarantee that the subsequent steps with the scouts doesn't drag me away into a local minimum, and I would miss the global minimum. This is my insurance policy that I'm still, okay, I maybe have an interest in this area, but I'm still checking out the other areas to make sure, like, oh, okay, you know, I'm not missing anything even more important. And then I iterate for, again, now this time from 1 to the max pop. This is to deal with the location of the scouts. What I do here, and this is sort of, I developed that as operational. I calculate M2 as half of the scout population. Why? I'm going to calculate the location of the scouts in 2 ways to give me a better grip or better search than just one way. Because initially I wasn't sure whether I want to do using uniform random numbers or normally distributed random numbers. And I said, well, if I split it in half, I can do both. So I calculate this count pop at JK. Now, I have my anchor is the value in pop I of k. And I want to go around it by time. Oh, okay, yeah. The difference here is this x high minus x low is the range times the step size that slows it down, and then this 2 times a uniform random number minus 1 ranges between -1 and 1. So I have this is my center value, and I am sort of going below and above it by this much. And of course, with each iteration, the step size is decremented. Then I check that the scout pop J of k is inside the trust region. If it's not, then I generate a random value within the trust region. For the second half, I use the normal distribution, where my mean is pop I of k, and then the standard deviation is the range divided by 3. You know, it's based on the 6 sigma. I figured, well, there's 3 sigma on one side, 3 sigma on the other side. That's why I'm dividing by 3 times the step size. So that will give me values normally distributed around pop of k. Again, I check the scout value, that it is within the trust region. If not, then I just generate a random number in that trust region. And then I calculate the function values for the scout population, and these are stored in column n+1. And then I append the rows of matrix scout pop with matrix pop. So I have now an augmented matrix. And I sort the augmented matrix pop using the values in column n+1. And then I extract the first max pop rows of the augmented matrix pop and store it back in matrix pop. So the second half is basically discarded automatically by this operation. And the best solution is in the first n columns of the first row. And the best optimized function value is in matrix element pop 1, comma, n+1. Now the algorithm has some design options. The first option actually is not specific to this algorithm, but it really helped. I designed a function called zoom range. The user should give a comfortable or relaxed trust region. But the problem is the wider you give it, the wider the ranges are, the more time the search is going to spend in useless areas. And so this function does statistical calculation and decides to shrink the trust region, shrink the ranges. This will help you to accelerate convergence, will speed up convergence also, so it's a big benefit. The other option is to normalize the variables so that they all fall in ranges of the same magnitude, not exactly necessarily the same range, literally, but the same magnitude. So if you have something like in the 1,000, you scale it down, and then you let the function worry about reverse scaling it as it does the calculations. Now, if you don't know how to scale the variables, you can run calculations with wide range first and see the results that come out and see what happens. And again, evolutionary optimization, you rarely just run it once. You run it several times and you tweak things, you fine-tune things. You can also Actually, if you get a value, you can then take that value and just tweak it, add a little bit, create really narrow ranges and run it again and get better values. Now you can divide the scout population into two segments like I did here that use different, two different random number generators. And actually you can create more than that, 3 or 4, whatever. And you can use different random generators such as Cauchy, modified Cauchy, empirical cosine, empirical sigmoid integral, and so on. Now, a lot of these, I looked at the distributions and I adapted them. I basically committed heresy. I think the American Statistical Association probably has a head out on me because I did. But the thing is, I played with it, and if it's giving me a distribution that I like, not necessarily replicating the normal, but around the middle, whatever, then it worked. And I tried different ones, and they seem to work okay. Some better than others. I can also imply 2 generations of scouts. So the pod lands in a place, that's the image I use, it launches a number of scouts, and these scouts in turn launches each one another generation of scouts. The hope is to get better accuracy. I think it did okay. My test function, I used relatively 3 simple test functions. The first one, f of x1, has the optimum solution at x of I equals I. And so for a problem with 4 variables, my trust region is, each variable has ranges from 0 to 5. The second one is f of x2. I got a little bit more complicated to test the accuracy, because sometimes it's easier to solve the first one, but if I demand more digits, that tells me how well the algorithm does. And the second one, the optimum is at x of I equals I plus I plus 1 over 10, I plus 2 over 100, I plus 3 over 1,000. And the initial trust region for this one is also between 0 and 5 for a problem of 4 variables. F of x3 has the optimum solution at x of I equals I square. So the initial trust region is between 0 and 25 for a problem of 4 variables. That's still, I would say it's still in the same magnitude. It's not like from 0 to 10,000 where it just kind of gets out of hand. Sample function call, the syntax of MATLAB, you declare function. The return value, best x is an array, a vector of the solutions, the variables that give you the optimum value. Best f of x is the best function value. And then the scout is the function name or variance of it. F of x is a handle of the function you're optimizing. Could be f of x, fx1, and so on. X low and x high are arrays defining the low and up ranges. Init step and fin step are scalar values, in our case, that define the initial and final step. Max iters is the maximum number of iterations. Max pop is the maximum number of pods, or the main population. Max scout pop is the maximum number of scouts for each pod. And then B semilog decay is a flag that says how I decay, reduce the step size, either semilog or log-log fashion. B skip narrow trust region is a flag that says whether I want to stick with the trust region I supplied or indeed narrow it down and to save time and effort. And then B trace is a flag if I'm curious as to what is happening and I want to see intermediate results at like 10% of the progress, not every single step. That'll be too much. And here's an example. The first one, I'm calling function scout, and this is the handle of fx1. The range is from 0 to 5. 0.1 is my initial step, 0.001 is my final step. I'm giving it 1,000 iterations. Maximum population is 100. Maximum scout population is also 100. Now, if I if I kept track of each population and each scout, I would have an array of 10,000 rows. Now, MATLAB can handle that, but if you go like a quarter, make it 500 by 500, you have 250,000 rows. I'm not sure MATLAB or any other software can handle that. So I'm limiting myself to one set of scout population. And these are the flags that will allow me to do semi-log decay, narrow the ranges, and then skip the tracing. And the narrowing of the ranges says new trust region, and it gives me the low and high value. And indeed they are within the expected solutions that appear here. 1, 2, 3, 4, as you can see. And then best X is 4.49, 10 to the minus 16. Very low value. The second problem is function fx2, the one that has a little bit more digits to test the accuracy. The arguments are pretty much the same trust region and the same operational parameters. It gives us a new trust region, again, pretty much similar as the other one, and it gives us the answer like 1.2345, 2.3456, and so on. And then 2.3 times 10 to the minus 14 function value, which is pretty good. The third one is similar, fx3, but instead of, the lower limit is still 0, but the upper limit is 25. And again, it reduces the trust region accordingly, and that really speeds up. I've noticed, instead of waiting for it a lot, it went faster. So investing the time to narrow the trust region is really worthwhile. And it gives you the roots 1, 4, 9, and 16, and 1.03 times 10 to the minus 16, very small value. Now, there's a PDF file in the proceeding and has like, 100 pages, and it's an extensive study. And all the Scout optimization algorithm versions did well. And the PDF file shows you the details on comparing between the various versions and indicate which are the top 3. The way I compare them is I compare them progressively, like I start with the first one and then the second one, so I compare the 2, and then the third one I'm comparing 3, and so on. So it was a progressive build-up. The proceeding also includes the MATLAB code for all the versions of the Scout algorithm, and an Excel file with Excel VBA version for, I think, maybe one or two selected versions. And that's all. Thank you.